Okay, so for the last two, yeah, I've mentioned this to you while we were doing that, but obviously this is not a maximum. It would have to be a minimum. It's just a typo. Okay, the graph's provided. We might as well use it just to see what kind of helpful information comes out. Each one of these tick marks here, it looks like pi over 6. So at negative pi over 3 and negative 5, that will be here on the graph. And at pi over 6 and 3, I will be up there. Okay, so if I wanted to do just a quick rough sketch of it, it would be kind of like this. So I might as well mark here that I have 3 and negative 5, because that will help me. From those two, I can figure out that the amplitude will be 3 minus negative 5 divided by 2. So that's 4. The center is going to be 3 plus negative 5. So that's going to be negative 1. So the other two pieces I still need to find are the phase shift and the period. Okay, so how can we find the period for this graph? Did anybody find the period for this graph? Jeremy, you want to enlighten us?
Period, I got pi.
That is correct. How did you do that?
The distance between negative pi over 3 and pi over 6 is pi over 2.
Okay, let me just draw that on my picture so people can see what you just said here. So this distance, okay, that is 1, 2, 3 times pi over 6 for the tick marks. So yeah, that distance is pi over 2.
And then the graph is only halfway finished, so we have to...
Right, so that's only half of the graph. Here would be the other side. So if it's only half, that means the full period would be pi. Okay. What about phase shift? How can we do a phase shift for this graph? Did anybody use a sine graph to model this? Yeah, did we use a cosine graph? Cosine graphs? Yeah, okay. Let's see, who did a negative cosine graph? All right. Connor, you want to tell us about it?
For a phase shift, I got plus pi over 3.
Plus pi over 3?
Yeah.
Right, because you went left pi over 3. So you mean plus pi over 3 is inside your equation?
Yeah.
Okay, yeah. So if you did the negative, here's an easy spot to, it starts pi over 3 to the left. So if you did negative cos, you could have said pi over 3 left. Did anybody do positive cos? Yeah, Catherine, can you tell us how you did positive cos?
I said the phase shift was 1/6 to the right, so...
Right. So here's the maximum. That's where a cosine graph would start. So pi over 6 to the right would work for a positive cos. Okay, so you may end up with a different answer than what we put up on the board here. But I'm going to assume that probably most of you would have picked the negative cos, so I'll go with that. But again, either would be correct. If the period was pi, what number would I have to put into here? Sure, Kara. Yeah, there's a 2. So how did we get that? Well, normally the period is 2 pi. So to get from, other way. To get from 2 pi to pi, that would mean I'd have to multiply by a half. So the number that goes into the brackets there would be a 2. The shortcut using the trig graphs, it would be 2 pi divided by the period equals the value that goes in there. So this would be 2 pi over pi, which is 2. Okay, so let's wrap up. Plus pi over 3. And the center line is negative 1. So that's one possible candidate. And again, there are many that would be correct for this graph. Okay. A Ferris wheel has a radius of 25 meters and its center is 27 meters above the ground. So I always find it helpful to start putting that stuff on a picture so that I don't have to keep remembering it. So this here it says is 27 meters, and the radius is 25. So I can probably mark in here that that's 52. And if I drop down by 2, I'd be at the height of 2. So if I wanted to model this, it says it rotates once every 40 seconds. So from there, I can get a period right away of 40 seconds. And it says she gets on at the lowest point when the wheel starts to rotate. So right there. Do you think it'd be more fun if the Ferris wheel, you got to get on at the top? Right? Like, do you think that'd be more fun? Well, you'd have to climb up like a giant, like, you know what I mean? And then you'd be way high up. And then getting into the chair, like, there's big consequences if you fall. So maybe it'd be, no? No? Okay, well, anyways, I'm sure most Ferris wheels get on at the bottom, but that's just an idea for those of you who are going to be engineers. So 40 seconds. From this information, I can see that the amplitude is going to be 25. And I can see the center line there of 27. So all that's left is for me to figure out the phase shift. If she gets on at the bottom, that's what the graph's going to look like from the lowest point up. So this is a negative cosine, and I won't have to do a phase shift if I use negative cosine. So y equals negative 25 cosine 2 pi over 40 x plus 27. And of course, the best answer we could include, we might as well simplify that down to pi over 20 plus 27. Okay, so determine the first time when Sandy will be 35 meters above the ground. So this is a picture that we're going to be looking for in our graphing calculator. There's her riding the Ferris wheel. And let's say 35 meters will be somewhere around there. So it wants to know the first time. And that's probably the first spot right there that I'll be looking for with the graphing calculator. Now, just so that everyone's clear, you can notice that this is actually quite a big job to do without the graphing calculator. There's quite a bit of algebra if you had to do this by hand, yet it's only worth 1 point. And the other one we just did is 3 points. So the reason it's cut down is they expect you to use your calculator, but part of that is that we also have to show them what we did. Okay, so you can write your answer down, but you need to support your work still in the written part of your test. So how do you do that if the calculator did it? Well, we just have to show them what went into the calculator. So here's how I would do this. I would show my marker that y1 on my graphing calculator is negative 25 cosine pi over 20 x plus 27, and that y2 is 35 meters. And then I would just give them a quick sketch of what I did in the TI-83. So in the TI-83, I would go second, calculate, and then intersect. So now the marker knows that I didn't just look at my neighbor's paper, that I actually, there was some strategy involved in calculating that answer, and I used the calculator, and here's how I did it. So if I put those values in and calculate the intersection, it looks like I get about 12.0 seconds. Okay, so that's how you're going to need to support your work when you do it in the calculator. If it was say like a formula that you used in your calculator or something like that, then you could just actually write what's on your calculator's screen. So anyway, as it becomes more relevant, I will show you again what's entered in the calculator. And if you're really like, oh, I don't quite get if this is supporting my work or not, look on an old provincial exam. You can Google for them. The old provincial exams, the answer keys look like this because they're showing how the answer key, the person with the key is expecting to see your calculator work. Okay, so if you really want to see exactly what the provincial examiners expected, take a look on Google, and we'll practice later in the year, but you may want to check it out now.